Okay, so let me review what we did last time. It was a lot to cover, but the upshot or the end point was we were looking at how to calculate, let's see if I can find the right word, how to calculate the intensity pattern from a light diffracting from a single slit. So here we again we imagine light is coming from the projector. It goes through a vertical single slit. I get a vertical line diffraction pattern, and what we were doing last time was to use the wave properties of light to calculate the interference of waves from different parts of the slit. So you remember that what we did was we divided the slit up into subslits, and we considered that what happened if we're looking at it at distant point P that determines the angle of the light reaching the point from the slit. We divide that slit up into subslits, and we look at the phase difference between adjacent slits, and we add them all up. And when we add them all up, we get a new amplitude. And when we square that amplitude, then we get the intensity at that point P. And that intensity or amplitude will change with theta, because the phase difference between these waves, adjacent waves, because of the different path difference. Remember, every time there's a path difference, which in this case is delta y times sine theta, there's a corresponding phase difference between the adjacent rays that are coming from the substrate. So we did this, and the end result was that we got this intensity equation. The equation that we derived was that the intensity at any given angle theta is equal to the intensity at 0 degrees times a factor that depends on theta. It depends directly on beta, but beta depends on theta. Right? And one way to remember what beta is, it's the phase difference between rays that arrive at P from the bottom of the slit compared to the, or I should say this, to the phase arriving from the top of the slit. So if there's a path difference d sine theta, then that corresponds to value beta. Either way, it's a functional form. It allows me to calculate I as a function of theta. So we'll work a couple examples of that. We'll also recall that this is very similar to the double slit equation, which we had before, which said that the intensity for the double slit, the intensity as a function of theta was equal to I0 times cosine squared of delta over 2, where delta is equal to 2 pi over lambda. Notice the very close similarity in the form between the two equations, and d times sine theta, right? And of course, this is path difference, this is phase difference. They're related by 2 pi over lambda. And d is the distance between the slits. And this is, of course, for called double slit. So double slit and single slit have similar types of equations that describe how the intensity changes as you go across the slit. Right? So I thought it might be useful to look at a couple of examples. Examples are always important. Every student on the end of semester forms always says work more examples. So I'll try to do that as much as I can. Okay, so let's look at one right here. This might give us a little bit of a feel for what's going on. Let's suppose, for example, that we have light of a certain wavelength. In this case, it's 700 nanometers. It's impinging on a single slit. It passes through a slit that's only 1 micron wide. You know, it's 10 to the minus 3 millimeters is 1 micron. And we want to know how wide in angle is the central maximum. So we know that the general form of the equation for a single slit is going to predict the shape of not only the central maximum, but all maxima. Okay? So, and this is given by I0 times sine squared beta over 2 divided by beta over 2 quantity squared. Okay? And then beta I'm not going to write out because it's very similar to this, but you replace little d with capital D. So this is our equation. And so the question now that they're asking is how wide is the central maximum? So basically what we want to know is that what is the angular, at what angle does the intensity go down to its first minimum? Remember, it's going to oscillate, so we're simply finding out where the first minimum is. Well, we know from what we did last time that the sine of theta, and I'll call it 1 for the first, and min for the minimum, is equal to lambda over d. Similarly, this point is going to be at sine theta 1 min equal to minus lambda over d, right? So we're going to have a symmetric distribution, and so all I have to do with this problem is to calculate lambda over d. So lambda in this case is 1 micron, and 750 nanometers is I'm sorry, I did this a little bit. I did this in an inverted way. I need lambda in the numerator. Sorry about that. 0.75 microns is lambda, right? I divide that by d, which is 1 micron, and that's equal to 0.75, and that's equal to sine theta, right? So we solve for theta, and I'm not going to write out all the subscripts again and again, but we get that sine theta min, sine theta 1 for the first minimum, is equal to 0.75, so theta is equal to 49 degrees. Okay. So that part is fairly straightforward. That tells me that an example of what angle, which in this case is the angle from the source or the slit to this angle theta, or theta 1, call it, right? Theta 1. All right, so that's all we have to do, and if we want to know how wide it is, then what I need to do is to take the distance L. So now I'm going to have to erase this so I can finish the drawing looking in a more reasonable way. So I want to then denote this distance L to the screen, and now I know that the distance y to the first maxima, or I'm sorry, the first minimum, is going to be equal to y equals L times tangent theta, right? Tangent theta 1. And in particular, the total width is 2y, so the full width 2y is equal to 2L times tangent theta 1. So if L is equal to 20 centimeters, 0.2 meters, times 2, and we can calculate what tangent theta is, but this example, it's worked out for us. It is 20.3. I don't have tangent theta, but I'll just put in tangent of 49 degrees, and I get that this is equal to 46, of order 46 centimeters. So the width of the central maxima is going to be equal to 46 centimeters. If I wanted to find out what the width of the first order of maxima, or the first fringe was, I would calculate the distance from theta 2, subtract the angular width theta 1. This angular width would be theta 2 minus theta 1, right? And I could calculate this width on the screen. So it's just a variation of that problem, okay? But basically, we use the fact that the minima of the this is called single slit diffraction. The minimum occur at d at sine theta sub m minimum is equal to m times lambda over d, and the maxima, so this would be the nth minimum, the nth maximum, so this would be for minimum, min, intensity, I. This would be for, if I want to know to review what it is for the nth maxima, it occurs in between the minimum, and it's m plus a half times lambda over d. Okay. So this would give me the equation for for I max, or if I use the same notation as I did there above, it would be the maximum for maximum intensity. Right? So these were where the minimum and maxima occur in the intensity pattern. Right? All right. Any questions up to this point? That's all kind of a review, but it's still important to go over it more than once. Any questions up to this point? Everybody's good? Makes sense? Yeah? Are you good with it? Yeah. So I'm going to erase this then, if everybody's already got this down, right? Okay. So read the problem while we're looking at it. Okay, so what the problem is, if I take this single slit diffraction pattern, right? This is the intensity versus angle, or intensity versus distance, however you want to write it. Distance on the screen. And I want to know what is the intensity of the first and second maxima as a function of wavelength and the slit width. In other words, what I'm going to ask is, what is the height of these maxima right here? Right? I want to calculate that. What is the height of this is the first order maxima, this one is the second order maxima. Right? So what is the height of this relative to the peak, to the central value? Right? And we're going to calculate because I of theta divided by I0 is exactly that quantity. I just need to make sure I evaluate it at the correct angle. Right? So I'm going to evaluate the correct angle to see what I get. So we'll try that. Hopefully I didn't destroy anything. I don't know why that. Yeah, it still works. Okay. So let's go ahead and try that. I'm going to erase this here. Oh, I erased one of my equations I was going to use, but I guess that's not too serious. I can rewrite that. Also, let me just point out here, I can use this drawing over here, right here, and note that what I'm interested in calculating is the intensity of this peak, and I know that the intensity of this peak can be described by d sine theta 1 max equals 3/2 times lambda, right? So in this case, m plus a half is equal to 3/2. Right? M plus a half is equal to 3/2. So this is the angle at which that maxima will occur, and I just want to find out what is the intensity of that maxima. So I'm just going to plug into this equation. Right? I'm going to use that value of sine theta in that equation and see what we get. Well, first of all, I have to calculate beta, right? So if I know theta, I've got to calculate beta, and then once I know beta, I can calculate I, right? So that's the path forward. Okay, so let's see. So I got sine theta 1 max, and that is equal to, or I should say, 3/2 lambda over d. And now let's calculate beta. How do I calculate beta? So beta is equal to 2 pi over lambda times d sine theta. D sine theta, bring the d on the other side. This is equal to 3/2 times lambda right? Notice that the lambdas cancel, the 2's cancel, and I'm left with 3 pi. Okay? So I know my value of beta, I can calculate. Notice, however, this is an interesting point, is that the intensity, which only depends on beta, does not depend on lambda or the width of the slit. Does not depend on lambda or d. Right? It's just equal to 3 pi. And similarly for the other ones as well. We'll work the second order maxima in just a second. However, notice that the location and angle does depend on lambda divided by d. So the general equation for the nth maxima is that sine theta m max is equal to m plus a half times lambda over d. So it does, the location depends on d, but the intensity does not depend on the wavelength. In other words, the question is how high is that peak, that first peak, the first side peak? That height does not depend on lambda or d. All right, we just found that beta is equal to 3 pi. So now we put this in here, and we'll notice that sine squared of 3 pi is equal to 1. And so I can evaluate this and say this is equal to I0 times 1 divided by, now I need beta divided by 2, and I need to square it. So beta divided by 2 would be 3/2 pi. And I square that, and that becomes 0.045. And that's my answer. I can evaluate it. I found that the height of the first intensity bump maxima, or the fringe we call it, is 4%, 4.5% of the peak value, and it does not depend on lambda or diameter at all. It'll be true for any single slit problem that we have. Okay. Now, I want to do the same thing for the second order maxima, and that's not too much different because I go through and now I have to recalculate beta for the second order maxima. So now I say that sine d sine theta 2, the second maxima, is going to be located when at an angle when this equation is valid or holds. Right? I'm sorry, don't need lambda over d here. I've already got the d. Or let's say sine theta lambda. Okay. So now we're doing m equals 2, so I'll put in 2 here. So 2 plus a half. So this is equal to 5/2 times lambda. Right? That's going to be d sine theta 2. So so now I've got to go through and calculate beta again. So beta is equal to 2 pi over lambda. Now it's going to be 5/2 lambda, right? So now d sine theta is equal to 5/2 lambda, and that is equal to 5 pi. Right? And once again, sine squared of oh, by the way, I did make a mistake without my beta over 2. Somebody didn't catch that. Sine squared of 3 pi over 2. Remember that you have to square the half angle, right? So this becomes 3/2. This is equal to 1, but this part is still correct. So the result is that beta, we need beta over 2, which is 3/2. Now we're doing the second order maxima, and for the second order maxima, this is going to be equal to, beta is going to be equal to 5 pi, and similarly, sine squared of 5 pi over 2 is equal to 1. Right? So what's the intensity of the second order of the sine of theta? We'll call it theta 2 max, which is the second maxima in the intensity pattern. And this is equal to 1 divided by 5 pi over 2 quantity squared. And that should be about 0.016. So, in fact, we can see that the drawing from the textbook is not done correctly. The second peak is not the same size as the first peak, it's 1/3. You see that? Now, the reason they drew it this way is they're just trying to give an idea, and because this is so small compared to this one, it was difficult to draw and still show you the physics of what's happening. But in reality, down this second one, and of course the third and the fourth and the fifth one keep getting smaller, right, as you go out. So this gives me a picture of the intensity pattern. Okay? Everybody with me so far? Any questions? Okay. 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 So that's the way we do this type of problem. I have one more example that I'd like to work that involves a two radio antenna. This is no longer, now we're not talking about single slit diffraction. We're going to go back and apply a problem in double slit diffraction. And what we're going to do now is to use an analogy. So remember that if I were to think of this as a double slit experiment, the way I would think about this is I would have light shining up from the bottom. I would have two slits, one where each of these black dots are, and only light can get through where those dots are located, and I'm going to calculate the intensity at different angles on the screen. Okay? What we're going to do instead is say, well, if this is a wave phenomena with interference, it should work for other phenomena that have a similar physical characteristic or setup. And in this case, I take two antennas that are popping vertically or horizontally out of the plane of the projector of the screen, and now I imagine that they are radiating sine waves, right? And this is a radio station that is emitting sine waves at whatever radio frequency wavelength that we choose to listen to. So now what we're going to do is say, well, now imagine that these spherically emitting or cylindrically expanding sine waves, the wave fronts of each of those are expanding out, and I want to calculate what is the intensity at a distant point at some angle theta relative to the geometry shown here of the two antennae. Okay? And so I can apply double slit equations to analyze this, but let's look at the questions. So imagine we have two radio antennas that are separated by some distance d, and I'm going to fix that so we can do a calculation. Let's say the distance between these two is 3 meters. Now it also turns out that if you were to listen to the radio station at 100 FM, 100.0 FM, that would be 100 megahertz. Right? 100 megahertz is a frequency on your radio dial, and so if I calculate lambda is c over frequency, right? The wavelength is c, the speed of light over the frequency. Then I would get that the wavelength of a radio wave is about 3 meters. So in this example, I've chosen the wavelength to be the same as the spacing between the slits, or in this case, the spacing between the antenna. So the idea here is that we have an analogy. I can consider the slits now as being replaced by antenna that are each radiating waves, but they have to be radiating in phase with each other. Okay? In other words, when this one emits away at the maximum amplitude of the sine wave, so does this one. Right? They're in phase. Okay? And that's a condition of the double slit. All of the theory we've done so far is that the phase at slit 1 has to be identical to the phase it's the phase it's slit to. Otherwise, I cannot calculate a phase difference at a distant point. I have to know what the starting conditions are. And the starting conditions are that the phase, at any instant in time, take a snapshot in time, the phase of the wave is the same at the 2 points. And that's also a property of double slit. Right? Okay, so we take two antennas separated by some distance. They're emitting waves. They have this wavelength, and now I want to calculate the intensity as a function of theta for various points far away from the antenna and find in which direction the intensity is a maximum, minimum. So the easiest thing to do, rather than just plot the whole thing out, is to calculate where are the maximum and minimum, right? Where are the maximum and minimum? So I can do that, and let's try that with the double slit equations. The equations for the double slit are cosine squared delta over 2. So this is clearly what we want to find. And now we want to find out what is I of theta. So we're basically asking this question. So let's draw a little picture. So our picture would be that imagine, so I have my antenna here and my antenna here, and it's separated by a distance d, and I'm looking at the intensity at a point P at an angle theta, and there's my intensity as a function of theta, and now I want to know where's the minimum? Where's the minimum occurring? Well, let's see. Here's my equations. What value do I want for sine theta? I want to choose the value of sine theta where the minimum occurs. So remember that halfway in between the two antennae, I'm going to get an intensity maximum, right? So this is clearly what we call I0. Right? It is going to fall off in a cosine squared fashion as we move away from the center line. So I want to know what is the angle at which it falls to 0. So I'll call this angle theta 1 min, right? And so the condition for a minimum intensity is that d times sine theta min, 1 min, is equal to, is going to be equal to m plus a half, m plus a half times lambda, because remember it's reversed, inverted with respect to the equations for single slit. So that's the one. Now I have to remember, does m start from 0, or does it start from 0, or does it start from 1? Well, the first maxima is going to be when this is in the first integer 1. So this is going to occur when m equals 0. Okay? So in other words, if the first maxima occurs at m1 times lambda, then the minimum is going to occur before that, because this is the first maxima over here, right? This is theta 1 max. So theta 1 min is going to be halfway closer to the origin. So I'm going to put in m equals 0, and so I'm going to get that d times sine theta 1 min is equal to lambda over 2. Okay. Okay. So let's see what angle does that occur for. Well, let's see. What we're going to do is we're going to get that sine theta 1 min is equal to 1/2 lambda over d. But in this case, lambda over d is 1, right? So we've chosen a case where lambda over d is equal to 1. So this is equal to 1/2. So theta 1 min is equal to 30 degrees. Okay? So that says that the first intensity minimum will occur at 30 degrees, right? If lambda equals d. Okay, so I've just calculated where the minimum occurs. Now generally, I don't want to have a minimum because this corresponds to, in radio reception, this corresponds to zero reception. There's complete cancellation, and I will not get a signal at all from the radio wave from my radio receiver set. Right? So I don't want to be able to see a point here. Right? I want this to move out to infinity. Right? So what is the condition for that to occur? The condition is going to be that sine theta 1 min must be equal to 1, or this angle, theta 1 min, must be equal to theta 1 min must be equal to 90 degrees. That way, at 90 degrees, it's 90 degrees is at a distance equal to infinity because it's measuring up from the horizontal. So I get this. So I get this simple condition, and so I say that 1 is equal to, and this minimum will occur when this condition holds. So I get that this is equal to 1/2 lambda over d. Let's see if I've done that right. So sine theta min, I want the theta min to be equal to 90 degrees. And so if it's equal to 90 degrees, then this sine is equal to 1. So yes, 1/2 lambda over d is equal to 1. And go lambda over d, so this will be sine of 90 degrees is equal to 1. So that says that the condition is that d must be brought in, or equal, in this case, equal to lambda over 2, which would be equal to 1.5 meters. Right? So if I have a wavelength of 3 meters, then the two antennas can be brought in to a spacing of 1.5, and at that point I will no longer get a minimum or reception or dead zone. And of course I can bring them closer than that, but I can't make them any further apart than that, otherwise there will be dead zones. It's a lot to sink in, but try to. Any questions? Want to ask a question? Going once, going twice. Okay, so great. Okay, now we get to the last part of the chapter, which is what happens when. See if I can do this without, yeah. Look, I think this deserves a picture first. What happens, up till now, let's review what we've considered. We've actually calculated the intensity for a single slit and double slit, but there was something unique about the double slit. The double slit calculation, the double slit had zero width, had slit width equal to 0. Right? How do I know that? Well, I considered what was the phase change as the light left the slit, and compared it to this one, but I didn't say where it left the slit. Right? So I assumed the slit was infinitesimal. That in fact the width of the slit did not really affect the intensity distribution at all. Right? Now we want to say what happens if I include the effects of a finite slit width in the double slit experiment. Right? So now what I'm going to do is say what happens if in fact these slits are open. So I'm going to use the same nomenclature. I'm going to say that the spacing between the slits is little d, and the size of the slits in both cases are capital D. So this has an opening of D, and this one has D. And in the cases that we are considering, it turns out that little capital D is always going to be less than, we might say much less than, not necessarily much less, let's just say less than little d. So in other words, we're considering only the cases where the width of the slit is small compared to the spacing between the slits. Right? So it's just the way I've drawn it here. Right? This slit is small compared to that slit. Now it doesn't have to be, but for the majority of cases that we will work out, sometimes to get familiarity with the equations, it's nice to be able to have a framework or a starting point. So I think this is a good starting point to have. So what happens when we make these finite slits instead of infinitesimal? Well, what the book tells you, and what all textbooks at this level will tell you, is that we're going to give you the answer, but we're not really going to derive it. Most of you are just as happy with that. Engineers like to use equations and apply them. They don't really care to what's being derived. And if you're a physics major, you will take an optics course later in your career, so you can learn more about it. Okay. So, order of simplicity, let's just state the result, and then we'll show why it looks normal or reasonable. The result is that when you look at a double slit experiment and you consider the slits to be finite width, then you end up with an intensity equation, which is the product of the single slit intensity pattern times the intensity pattern of a double slit. In other words, the two are multiplicative. Right? So we now have a very simple answer to the problem, which is that to include this effect, we simply multiply the single slit intensity pattern times the double slit intensity pattern. Right? Looks very simple, and that is in fact the end of the story. Right? There's a couple things you can actually convince yourself of to make sure that this is reasonable. Imagine that you take the limit in which the spacing between the slits goes to 0. When that happens, I should get single slit. Right? If I take the two slits and I merge them closer like this, then eventually they overlap and it becomes just one single slit. Right? That's the limit in which, in this equation, in which delta goes to 0, and in fact cosine squared of 0 is 1, and in fact I do get simply the single slit intensity pattern. So in the limit that the spacing between the slits goes to 0, I recover the single slit intensity pattern. In the limit that the spacing between, that the openings of the slits go to 0, I should in fact just get the cosine delta over 2 term. In other words, it becomes the traditional double slit pattern with 0 slit width. Right? And so I can do that by taking the limit at beta, which beta goes to 0, because when the slit width, capital D, goes to 0, then beta goes to 0, and we've already shown, or you can show by L'Hopital's rule, that when you take the limit of sine x over x as x goes to 0, the answer is 1. Use L'Hopital's rule, and you can show the limit that the calculus shows that. So then this becomes 1, and then I theta equals I0 times cosine delta over 2 squared. That is, in fact, the intensity pattern of a double slit with 0 slit width, which is, in fact, what we derived when we ignored the slit width, and we got I equals I0 times cosine, and this term is 1. So it agrees, right? We've just verified that in the limit of 2 conditions, it seems reasonable. It gives the right answer, right? And then you take it on faith, of course, that it, or through experience, that it gives you the right answer and all other values in between. But that's a 3-hour lecture, and we're not going to do a 3-hour, proof of that equation, right? And again, I want to just emphasize that the intensity versus theta as before is proportional to the square of electric field amplitude, because that's how we calculate these things. That's an important factor, property. And this is a property that we will use in quantum theory as well, when we calculate the intensity pattern of electrons that actually diffract just like waves. And then we'll find out that their wave property is explained by using this principle that intensity is proportional to the field, electric field squared. Anyway, all right, so the only equation that's not left out up here is delta, but that's over here. It's basically, remember, beta and delta are the same equation. You just replace capital D with little d, and that's how you get the delta instead of beta. So there's only 3 equations to memorize, not memorize, you use. The intensity equation, how to calculate beta, and how to calculate delta. And of course, delta is, like I just said over here, it's written down in your book. You know, we've already derived that. That's the same. 2 pi over lambda times little d's. Okay. So, final example. One thing I should mention first before we do this. So you remember that early on in this chapter, we showed you a picture of, I showed you a picture of the double slit intensity pattern with 2 slits. And you remember that when we did the derivation, we got these interference peaks. These interference peaks occurred with equal amplitude because it's basically cosine squared, delta over 2. And I said this decrease, the fact that these peaks actually get smaller is due to the fact that we have to include the width of each of the slits. And so now that we have an equation that describes that with finite width, which is this equation, if I plot that equation out, by the way, which I'm going to do here right in this one, I get this blue function on the lower curve. So this one is what we call the diffraction factor, or the diffraction envelope. This is the envelope of the cosine squared term that you get from double slit diffraction. So if we want to learn how to plot that function I just showed you, then what we do is we multiply the cosine squared term, which is the double slit diffraction, by the sine beta over beta term, which is the diffraction pattern. And this provides an envelope for this oscillation. And if I apply this envelope to this oscillation, I get the third curve, which in fact is exactly what that function looks like. So when I plot now the intensity pattern for a double slit experiment, in which I include the fact that each of the slits are finite and they're separated by some distance, then I get this curve, this oscillatory blue curve, which dies out and then it picks up again, and then it dies out and it picks up again. Okay? So this describes that phenomenon. And that's a plot of the equation we just showed you. If I look at the actual experiment, then what I would see in the central peak, the central diffraction peak, this is, remember, a modulation due to the width of the first peak, of the width of the slits. Then this are called the diffraction peak, which is due to the oscillations of the double slit. So here I have the double slit oscillations, and these peaks occur exactly where we predicted from the double slit experiment. But now the peaks are modulated and they oscillate up and down, given by the envelope of the single slit equation. So what I'm actually showing here is that the experimental results show you, in fact, that the intensity is dying out, that the peaks are getting smaller, and that's sort of what you see. If I took a line profile through this screen, I would see the intensities increasing and going up and down from 0 to maximum, 0 to maximum, but at reduced intensity, until I get out to the minimum of the single slit diffraction peak, and that's where this black line is, and that's where this intensity on either side goes to 0. So I'm only plotting out the distance from the first black stripe to the second black stripe on the left to the black stripe on the right, and nothing beyond that. So you're just seeing what's in the number of and the shape of the diffraction peaks, or I'm sorry, the interference peaks within the central maximum of the diffraction peak. So we have a nomenclature that, or language, a language vocabulary that is important to learn. And that is, we refer to these peaks as diffraction, as interference peaks, or as you see here, interference factor, cosine squared delta over 2. We refer to this shape as the diffraction factor, or the diffraction. So this is the minimum of the diffraction peaks. And this is due to single slit. So single slit, we refer to as diffraction. Two slit variations we refer to as interference. So I talk about the interference peaks, which are these, or I could talk about the diffraction peaks, which are these. It's a little confusing. I could use the word single slit and double slit instead of those two, but just to let you know some of the problems in the text use that language. Okay. Okay. Okay, so as a final example for this chapter, let's try a problem. This particular problem is the following. Let's suppose that I'm looking at a double slit experiment. The slits have finite width to them, so in fact, maybe I can just lift this whole thing up. And I want to know, I have a, let's look at the condition. So the condition is I have a double slit experiment, and I have a certain width, and I have a certain spacing. Right? So the spacing between the slits is little d, and the opening between the slits is capital D, I mean the slit width. Right? And what I'm asked to calculate now, what we're going to calculate, is how many diffraction interference peaks are there. So let's look at the diffraction envelope. This is the single slit diffraction envelope, right? And within that, I have the double slit cosine squared modulation term, right? This is the cosine squared modulation term, right? And of course, it's symmetric on both sides. I won't draw it out. And I'm given a certain condition that the spacing between the slits, little d, is equal to 6 times the opening of the slits. So the opening of the slits is 1/6 of the spacing. Right? And now the question is, when I calculate, is how many interference peaks are contained within the central diffraction peak for this particular ratio. In other words, the question that I'm asking is, I want to know that this is the central maxima of the diffraction peak. I want to know how many diffraction maxima are there between this theta min and this theta min. In other words, how many of these peaks are there in here? Right? Without just, of course, counting them up. That's obviously not what we're trying to do here, right? We count them up and get the answer. The question is, if I change this to d over 6 is equal to 4.3, then you wouldn't be able to just count them on the graph. So we're going to find a way to calculate it, right? Okay, so what are the equations that we have? Well, first of all, we have that capital D times sine, the condition is that there's a maximum angle that we are considering here. And that is what I'm going to call theta 1 min. So this is where the first minimum occurs in the interference peak, in the diffraction peak. So I have d sine theta 1 min is equal to m times lambda, but m is equal to 1, so this is equal to lambda. Okay. The condition for a maxima, the nth maxima for the diffraction peaks, the nth maximum will occur for d sine theta sub m equal to m times lambda, right? And this, of course, will be the condition for the nth peak of the interference pattern. Right. Okay, so let's write that out. That says that d times sine theta m maximum, where this refers to the double slit condition, is equal to m times lambda. Right? But we know that little d is equal to 6 times the spacing. Right? So that I can replace this with 6d times sine theta m maximum equals to m lambda. And let's see, I'm trying to think of the simplest way to explain this. So there will be, I can use this equation now as well. So I can use this equation 1 and 2. And if I divide 2 by 1, then I get 6 times sine theta m maximum is equal to, this divided by sine theta 1. D, 6d, I'm sorry, 1 second, 6 theta m maximum divided by sine theta 1 minimum is equal to m. All right. So we can see then that for m equals 6, which is the 6th diffraction or the 6th interference maxima, then I have the condition that sine theta m max occurs exactly at the same angle as the further minimum of the diffraction pattern, sine theta 1 min. Okay, so that means that the 6th diffraction, the 6th diffraction maxima will occur at exactly the same angle as the first 6th interference maxima will occur at the exact location as the first diffraction maxima. Diffraction minimum, sorry. This is going to a 0, right? So what that says is that since the intensity is the product of the two terms in the whether it's the sine squared of one with the cos squared of the other. Let me draw a picture for you. Since the intensity is the product of these two, then the 6th interference maxima is being canceled by multiplicative term of 0 on the envelope, which means that the 6th maxima is suppressed, and the intensity here, intensity is equal to 0. So the 6th maxima does not show up. It is crushed by the envelope of the diffraction modulation, and so that leaves that there's only 5 fringes between the central fringe and the first minimum. So that says that there are going to be 5 interference peaks above and below center line, plus 1 for the central maximum. Okay. So that means that there will be 5 of these peaks above between 0 and theta min on this side. There'll be 5 fringes on the other side, plus the one in the middle, which is the central. That's this one right here. This is the central maxima. And therefore, the answer will be 2 times 5 plus 1, or 11 fringes. So there'll be 11 maxima between minus 6 degrees, which is where the first minimum occurs in the single slit in pattern, and plus 6 degrees, which is the other side of the central maximum. Right? So we just found a way to count them up. This is all designed to help you get some feel for the equations. Yes?
You were just setting the sine theta max equal to sine theta min because you're only doing the center diffraction, so you're...
What are you talking about here?
Yeah.
No, I'm looking at side bands. So these are side bands. These are fringes. I'm only looking at fringes. I'm going out away from there. And I'm saying, how far out can I go? What's the largest maxima of the interference before I hit the end of the central peak?
So they know the min and the max will be at the same, will be equal because...
They turn out to be equal because when I take the ratio, there's 2 equations that are governing this. One is the equation for the this is the equation for finding the minimum of the single slit experiment. This is the equation for finding the maximum of a 2-slit experiment. And so when I substitute in the ratio, you get from this equation that when m is equal to 6, that the sine of the 6th maxima occurs exactly where the angle of the minimum of the diffraction peak occurs.
Yeah, I think I get it, yeah. They're just occurring at the same...
At the same angle.
Yeah.
Yes, yes. So basically, what they're saying is there is a 6th peak here, but it gets suppressed because the envelope is crushing it down to 0.
At the same time that the single slit is.
Yeah, but the single slit produces a 0 intensity at this point. The double slit should, by itself, should have a peak right here, but it gets suppressed.
Okay.
So the 6th interference peak occurs exactly at the minimum of the first single slit minimum. So, in fact, if you count these, 1, 2, 3, 4, 5, and then the 6th is suppressed. So you got 1, 2, 3, 4, 5, the 6th is suppressed. So I've got 5 peaks to the left of center line within the central envelope, and I've got 5 peaks to the right within the central envelope, and I've got 1 in the middle, making 11. Okay. Yeah, it's a lot to absorb. I mean, it's really study, study, study. That's all I can tell you. You know, study, study, study. Spend your time with your book, going over this and looking at the slides, and of course, doing the homework and working more than just the 6 homework problems. Look at other problems in the book that have answers for you the odd number answers that are similar and say, could I work this one? You know, it might be number 7 instead of number 8 on the homework. You know, that'll help you fill in any gaps you have. You know, you want to be able, when you finish a problem, to go back and say, what was I trying to learn here? What equations were I using? And how could I ask the question differently to get solved for a different parameter? Because that's probably what I will ask you on a test. Is I'll take one of these problems and I'll ask you to find a different parameter, use this equation to find a different type of solution or a different answer using the same equation. Six hours a week, guys. 6 hours a week, that's the best I can tell you. And work with someone. It's always good to try the problem yourself, then find a study buddy, you know, say, you know, let's talk about problem number 7, did you get that, or number 8? And then that's, you know, feeding off of each other for discussions is a good way to learn. If you continue. Okay. It's hard. I mean, I'm not going to lie to you. This is stuff that is really tricky, and it's easy to get confused on if you don't spend some time, you know, thinking about it. It really is. I'm not trying to scare you. Sure wasn't. Okay, we are done with that chapter. So let's see what we can find. Yeah, so you know what I think I'll do, I don't need to bring up the slides for this. Let me give you a handout that they brought. There's another example that's in the next chapter. You can just pass those back as we go through. And don't forget to bring this to you with you on Tuesday, because chances are we're not going to get through it. We'll just give you a chance to do it. That's all I have. Just keep passing them over to you. Now, let me just say briefly, the topic is the Michelson-Morley interferometer. And it's an experimental device. It was the first time an American was awarded the Nobel Peace Prize in something like 1895 or something like that. It was one of the first Nobel Prize experiments. And it turned out to be very critically important in the study of relativity. And Einstein called it the single most important experiment done to confirm the theory of relativity. Even though at the time he was developing it, he was not aware of the results. Have you guys got enough to pay? There should be, we're out?
We have 2 different types.
Oh, shoot. Okay. I knew there was something wrong with the copier when I started by getting it. Okay, I'll have to use the whiteboard until I'm ready. Sorry, guys, we're not going to be able to do that. The one I'm going to start with, I don't know if you could share with somebody. It's the first one that says Michelson-Morley on it. That's page 1. I'll have new handouts for you. Don't worry when you come back. So the basic idea is that Michelson and Morley had a light source that was incident on a half-silver mirror, and the light that hit the mirror, we call this a splitter mirror, M sub s, and we have white light wavelength lambda that's impinging on it, and the light is reflected in 2 arms. So we have light coming in this way, it goes up to here, it comes back down, so it's returning, and so it comes back down, it reflects off here, and the combined beam from the 2, so I get one of the reflected waves from M1. You can probably see this on the drawing a little bit better than I'm going to explain it right here. So I've got light from M1 that goes along an arm that's of length L1, and I have light that goes from up to M2, which is a second mirror, which of length L2 away from the splitting point. And when the waves come back, so the light comes back this way, it goes up here and comes back, and then it recombines when it gets reflected or transmitted through from mirror M2 or reflected from mirror M1, and I get a sine wave for the electric field that is reflected from M1, and I have another one that is reflected from M2, and I'll draw that a little bit displaced from the first one, like this, right? And what the first story, or the first thing to remark in this experiment, is that because we're recombining light waves that traveled either the same or a different path length going up to the mirror and back, then the light, when it collects together again, will either be in phase or out of phase. So let's consider a condition where L1 is equal to L2. That is to say that the light that gets transmitted through the half-silvered mirror to M1 travels the same distance as the light that goes up to mirror M2 and comes back. Then the two light rays will have traveled the same distance going up and back. Since they have traveled the same distance, they will be in phase when they get recombined. And as long as they travel the same distance, they will be exactly in phase. If, on the other hand, I now move this second mirror, and by the way, when they recombine in phase, I get what would be called a bright spot, or in other words, whatever spot I have of light coming in through the first mirror, I will see in the reflected system right down here. If, on the other hand, now, what I do is I move this mirror M2 up by a distance lambda over 4. By lambda over 4, then, and I'll call that distance delta x, then the path difference is going to be equal to 2 times delta x. Is equal to 2 times delta x. Why? Because the light has to go up till it hits the mirror and back, so it travels an extra distance delta x going up, an extra distance delta x coming down. So the total path difference is 2 times delta x. What is the phase difference? How will I calculate? You make me think about what formula I'm going to use to calculate the phase difference.
2 pi over lambda.
Okay, what is it? Delta phi equals 2 pi over lambda times what? Huh?
And delta.
How is path difference and phase difference related? Huh?
D sine theta?
There's no sine theta here. There's no theta. But d sine theta represents a path difference. What is the path difference? For if this one, if this gets moved up a distance delta x, what's the extra path length that this light has traveled relative to that one?
Delta L.
It's delta L, and how big is delta L with respect to, is it equal to delta x?
It's
2. Why 2?
Because it goes up and down.
Up and back, right. So 2 pi over lambda times path difference. Path difference is equal to 2 times delta x. Right? When delta x is equal to lambda over 4, right, then the phase difference between the two waves, right? We're talking about the phase difference of these two waves when they recombine is going to be equal to this quantity. But this is actually then equal to, the phase difference is equal to pi. Right? What happens when I add two waves that are 180 degrees out of phase with each other? What do I get? Nothing. 0. So now I move it. If I move this up a distance lambda over 2, the bright spot becomes a dark spot. Full cancellation. Okay? What happens now if I move it another distance lambda over 4? So I moved it up lambda over 4. Now I'm going to move it up lambda over 4 again. Right? Now what's my total path difference? I moved it up lambda over 4, but then moved up lambda, so I moved it up a total of lambda over 2, right? What's the phase difference when one wave travels a distance lambda over 2? Well, further, this is the equation, right? So now the phase difference is 2 pi over lambda times lambda. The total path difference is going to be equal to lambda, right? Because I get lambda over 4 plus lambda over 4 going up, and I get lambda over 4 plus lambda over 4 going back down. And so that total path difference is equal to lambda. Right? I better get a bright spot, because two waves that are exactly one wavelength out of phase with respect to each other will give you double amplitude, right? It gives you maximum brightness. Does it work? Well, here's my path difference. 2 times delta x is equal to 2 pi. Yeah, and the phase difference between two waves is 2 pi. They're going to add constructively. So now the bright goes to dark becomes bright again. It becomes bright. So as I move the mirror up lambda over 4, it gets dim. Then I moved up lambda over 4, it gets bright. What happens if I go another lambda over 4? It gets dark. And then it gets bright. Right? Right? So now I'm going to look at what happens if I do that 100 times. I go through 100 cycles. We'll talk about that next time. But that's the general idea. Everybody got this? This is the general idea of interference for the Michelson model. We'll go through a little bit more next time. Okay. See you all Tuesday.